Okay, so this is one of the Holt-Winters models. This is the additive model with no trend. And I'm just going to kind of work through this as the book example, as one of the book examples. Um, so just have a look at our data. We have 2 years data. We have data for January to December for each of these 2 years for gas consumption. Now, one of the interesting things is, as there's only 2 years, um, when we when we utilize the seasonality, we're using our first initial kind of estimate of seasonality um, in the forecasts, and then we update the seasonality, but we're not going to use those updated seasonalities, and this will have an interesting effect when we optimize. But we'll talk about this later. So the first year is where we have almost the burn-in period, and the second year is where we make the forecasts. So we have an initial, in the burn-in period, we have an initial estimate of the level. And we just estimate this as the average of all the kind of the usage. So this is our estimate of the level. And I'm going to put dollars here because I'm going to just drag this down. So you see this was similar to the previous season, the seasonal regression example, in that January we have a lot of gas used and August we have very little, but our general non-seasonal level is the average of all of these, 105. And once we've got this average, we can make an initial attempt at, an estimate of the seasonality. And this is just the gas use in a single month subtracted from the level. So we just drop that down, and you can see January, February, and December, we have much higher gas usage. And then the summer months, particularly from like June through September, we have much lower gas usage. Now, we're going to update using the equations. This is equation 912 on page 343. And so what I'm going to do is I'm going to do equals, and then we have the alpha, which is the update of the level. And let me just put a dollar here as I'm going to drag it down, multiplied by the current value minus our current estimate of the seasonality, which is going to be this here, plus 1 minus alpha, so 1 minus D4, and we're going to multiply it by our kind of previous forecast. And we multiply this by the previous level. So the first part of the equation is just alpha times the new update of the new estimate of the level versus 1 minus alpha, the previous update of the level. So this is kind of similar to the basic exponential smoothing. And this gets 100.15. And then we're going to have our new estimate of the seasonality. And this is just going to be equals, and again, it's going to be updating using a smoothing. So it's going to be our gamma multiply our current estimate of, based on the current information of the seasonality, which is just the actual value minus the level, plus 1 minus alpha, again just use the dollars, times by the previous seasonality. And that gets us 130, which actually fits in with what was in the book. and then the forecast. And remember this, we're updating given the current data, but the forecast has to come from the previous values. The forecast is basically the previous level for the previous period, plus our previous estimate of the seasonality. And this is the seasonality from the last January, so the last equivalent period. And so our estimate here is 244. And finally, our absolute deviation is going to be the actual minus the forecast. And of course, we do absolute. And it's 14. Now we can just drop this all the way down, assuming I've put enough dollars in there. And so here, let's just look for example. So for this one here, we do the current, this value here, minus the most recent estimate of the seasonality. And this gives us the current updated level times alpha, plus 1 minus alpha and the previous level. And again, this is updated. We have the seasonality. And here it's going to be my gamma times C24 minus D24. So this is my current difference of the current from the level, which gives me my current seasonality over 1 minus gamma with the estimate of the previous seasonality. And finally, the forecast is the previous level and the previous seasonality. Seasonality, we need to go further back because obviously it's a seasonality from the last July. A few little things. If you look at the book, I agree with the book up to April. But if you look at May, this is figure 19 in 345, they have 55 minus 105 equals minus 31. And that is an error in the book. And in fact, I just checked with the spreadsheets, and they actually included a revised version in the book spreadsheets, which agrees with which kind of what I did. So the book numbers are actually erroneous. And then we could actually, forecast further down if we wanted to. So we forecast here. And again, we're just taking the last value of level and the last seasonality. If we want to do any kind of drag down and make forecasts further in advance, we could just put $1 so we can kind of drag this last level down further. And then, for example, here we could do a 2 additional. Okay, so let's kind of draw the graph that we got on page 345. And here what we want to do is we want gas use, and we want gas use. Okay, third time lucky, gas use, control, and then the forecasts of gas use, and then insert, and a line graph, and I'll say this forecast of gas use. And let's just add some axes. That would just be period. And then gas use. Okay, now let's optimize this. So what we want to do is let's go to data solver, and we want to minimize the mean absolute error. So let's actually for the absolute deviation. So we'll do the MAD, mean absolute deviation, and that's just going to be the average of all of these errors. And so what I want to do is data analysis. No, sorry, I don't want to do data analysis. I want to do a solver. And I want to minimize this value. And I'll minimize by changing alpha and gamma. And again, these smoothing parameters are always between 0 and 1. We're saying they're non-negative, so we've included the greater or equal than 0 already. And I'm going to click OK. And that's my optimization. So minimize the mean absolute deviation by changing the alpha and the gamma, making sure that they're all between 0 and 1. And you see my MAD is lowered. You can also see that the forecast actually very closely hit the actual. Now, I almost feel that this is because of how the data may have been generated in an artificial manner. So it was almost very similar from the first year to the second year, and maybe taking just random errors off. So if basically any tuning would be tuning to random error and would actually negatively impact the next forecast. So the fact we have an alpha of 0, I think generally a real world application with multiple years, you shouldn't get an alpha of 0. And this gamma doesn't change, and that literally is because here we're calculating our first set of seasonalities with the gamma, but we only actually use them in the forecast for the year after, and we don't have the data for the year after, so we can't evaluate. So we can't actually optimize the gamma. That would have been 0.9, pretty much whatever the data is, unless we added an extra year. Okay, so that was additive Holt winters with no trend.